Hello again. Um, I was uh, I was planning to not stream today because I'm I have some stuff to do today. Not today, but tomorrow. But I decided to just uh, try to not skip this day, even if I do only 1 hour or two, for example. It will be just it counts as a day, so that's that's what I'm trying to do. So let's continue with this. Last time we stopped here in chapter 15, address translation. After we learned about what is an address space and some stuff about the memory API, which I already knew, except that the fact that malloc is not necessarily a syscall. It uses a syscall under the hood, but uh, it's not like it's a syscall on its own. Sometimes it will manage your dynamically allocated memory just in user space because it has a lot of already allocated chunks in you understand. I don't know how to describe it because I still stuck at English, but I will get better, hopefully. Heard also that a lot of people who did not speak English well uh, became good at it just by forcing themselves to speak, and they get familiar with it, and they're like they get used to muscle memory of the tongue or whatever, or however, uh, or whatever you can call it. And I wish it will get better soon. So, okay, address translation. This part is about the mechanism of translating the virtual memory into the real memory. How does the hardware and the kernel help do that? Okay, so in developing the virtualization of the CPU, we focused on a general mechanism known as limited direct execution, or LDE. The idea behind LDE is simple. For the most part, let the program run directly on the hardware. However, at certain key points in time, such as when a process issues a system call or a timer interrupt occurs, arrange so that the operating system gets involved and makes sure the right thing happens. Wait, in the CPU focused on general mechanism. Okay. The idea behind LDE, limited direct execution, for the most part, the program ran directly on the hardware. However, at certain key points in time, which is system call, okay, arrange so that the operating system gets involved and makes sure the right thing happens. Thus, the operating system with a little hardware support tries its best to get out of the way of the running program. To deliver an efficient virtualization, however, by interposing at those critical points in time, the ISO ensures that it maintains control over the hardware. Efficiency and control together um, are how two of the main goals of any modern operating system. In virtualizing memory, we will pursue a similar strategy, attaining both efficiency and control while providing the desired virtualization. Efficiency dictates that we make use of hardware support, which at first will be quite rudimentary, just a few registers. It implies that the operating system ensures that no application is allowed to access any memory but its own. Thus, to protect applications from one another and the operating system from applications, we will need help from the hardware too. Finally, we'll need a little more from the VM system, virtual memory system. In terms of flexibility, specifically, we'd like for programs to be able to use their address space in whatever way they would like, thus making the system easier to program. And thus we arrive at the refined crux. Wait, let me ask, how do you pronounce crux? Crux. Box, ducks, crux, trucks, crux. Okay. So the crux, how to efficiently and flexibly virtualize memory. How can we build an efficient virtualization of memory? How do we provide the flexibility needed by applications? How do we maintain control over which memory allocations and applications can access? Of course, ensure that the application memory accesses are properly restricted. How do we do all of this efficiently? The generic technique we will use, which you can consider an addition to our in addition to our general approach of limited direct execution, is something that is referred to as hardware-based address translation. Or just address translation for short. With address translation, the hardware transforms each memory access an instruction to fetch, load, or store, changing the virtual address provided by the instruction to physical address, where the desired information is actually located. Thus, on each and every movement memory reference, an address translation is performed by the hardware to direct application memory references to their actual location in memory. Of course, the hardware alone cannot virtualize memory, as it just provides low-level mechanism for doing so efficiently. The operating system must get involved as key points. To set up the hardware so that the correct translation takes place. It must thus manage memory, keeping track of which locations are freed and which are in use, and judiciously intervening to maintain control over how memory is used. Once again, the goal of this work is to create a beautiful illusion that the program has its own private memory where its own code and data reside. Behind that virtual reality lies the ugly physical truth that many programs are actually sharing memory at the same time. And the CPU switch between running programs and the next through virtualization. The operating system, with the hardware's help, turns the ugly machine reality into a useful, powerful, and easy to use abstraction. Hmm. Assumptions. Okay, our first attempt at virtualizing memory will be very simple, almost laughably so. Go ahead, laugh all you want. Pretty soon it will be the operating system laughing at you. When you try to understand the ins and outs of TLBs, multi-level page tables, and other technical wonders, don't like the idea of the of well, you may be out of luck then. That's just how the OS rolls. Specifically, we will assume for now that the user's address space must be placed contiguously in physical memory. We will also assume for simplicity that the size of the address space is not too big. Specifically, that it is less than the size of physical memory. Specifically, that it is less than the size of physical memory. Finally, we will also assume that each address space is exactly the same size. Wait. Specifically, we'll assume now that the user's address space must be placed contiguously in my physical memory. Okay. The address space will be placed contiguously in physical memory. We will also assume for simplicity that the size of the address space is not too big, specifically that it is less than the size of physical memory. Okay, we will suppose that all the address space will fit in the physical memory. If we subtract other stuff that exists, okay? Finally, we will also assume that each address space is exactly the same size. Each address space is exactly the same size. Don't worry if these assumptions sound unrealistic, we'll relax them as we go. Thus, achieving a realistic virtualization of memory. An example. Okay, so what are our assumptions? Address spaces of multiple processes are the same size and are not too big and must be stored contiguously in real memory, in your physical memory. Okay, let's take an example. To understand better what we need to do to implement address translation and why we have such a mechanism, let's look at a simple example. Imagine there is a process whose address space is as indicated in figure 15.1. What we are going to examine here is a short code sequence that loads a value from memory, increments it by 3, and then stores the value back in memory. And then stores the value back into memory. You can imagine the C language representation of this code might look like this. The compiler turns this line of code into assembly, which might look like something. Okay. Load, okay. This code snippet is relatively straightforward. It presumes that the address of X has been placed in the register EBX. And then it's straightforward. It presumes that the address of X has been placed in the register EBX and then loads the value of that address into the general purpose EX using the move instruction. Long word, move long. The next instruction adds 3 to AX, and the final instruction stores the value in AX. back into memory at that same location. In figure 15.1, page 4, observe how both the code and data are laid out in the process address space. The three instructions code sequence and the value of the variable x in the stack near the bottom. In the figure, the initial value k as shown in its location on the stack. When these instructions run from the perspective of the process, the following memory accesses take place. Fetch instructions at address. Okay. The entire page just for this. Right. Interposition is a generic and powerful technique that is often used to great effect in computer systems. In virtualizing memory, the hardware will interpose on each memory access and translates each virtual address issued by the process to a physical address where the desired information is actually stored. However, the general technique of interposition is much more broadly applicable. Indeed, almost any well-defined interface can be interposed upon to add new functionality or improve uh, some other aspects of the system. One of the usual benefits of such an approach is transparency. The interposition often is done without changing the interface of the client, thus requiring no change state to client. Does this like say that interposition is just like being having a middleman? In figure 15 point, okay, fetch instruction, execute this instruction. Uh, okay, fetch instruction, execute this instruction, fetch then the instruction, execute this instruction. Okay. Operating system not in use, code heap, relocated process. From the program's perspective, its address space as address 0 and grows to maximum of 16 kilobytes. All memory references it generates should be within these bounds. However, to virtualize memory, the operating system wants to place the process somewhere else in the physical memory, not necessarily at address 0. Thus, we have the problem. How can we relocate this process in memory in a way that is transparent to the process? How can we provide the illusion of a virtual address space starting at 0, when in reality the address space is located at some other physical address. An example of what physical memory might look like once this process. I am literally reading without understanding anything. I cannot understand anything. Like I read paragraph and I realize I didn't understand anything that I have read. It's been just 20 minutes. I have, it's always like this. I feel it's been like the same thing in all the previous streams. Like after 20 minutes of starting stream, I feel like my brain is just shut down, stopped working. I just always check how long have we been streaming after around 20 to 23 minutes. Just like it's my brain's physical limitation or something. Okay, so from the program's perspective, its address space starts at 0 and grows to a maximum of 16 kilobytes. All the memory references it generates should be within these bounds. However, to virtualize memory, the operating system wants to place the process somewhere else in physical memory. Not necessarily at address 0, and thus we have the problem. How can we relocate this process in memory in a way that is transparent to the process? How can we provide the illusion of a virtual address space starting at 0, when in reality the address space is located at some other An example of what physical memory might look like. Okay, process is figure 15.2. In the figure, you can see the OS using the first slot of physical memory for itself, and it has relocated the process from the example above into the slot starting at physical memory address. The other two slots are free. Dynamic hardware-based relocation. To gain some understanding of hardware-based address translation, we'll first discuss its first incarnation. Introduced in the first time-sharing machine of the late 1950s, is a simple idea referred to as base and bounds. The technique is also referred to as dynamic relocation. We'll use both terms interchangeably. Wait, what? To gain some understanding translation, we'll first discuss its first incarnation. Introduced in the first time sharing machines of the late 1950s, is a simple idea referred to as base and bounds. The technique is also referred to as dynamic relocation. We'll use both terms interchangeably. Base and bounds. Specifically, we'll need two hardware registers within each CPU. One is called the base register, and the others are bounds, and the other the bounds. Okay, the base and bounds pair is going to allow us to place the address space anywhere we like in physical memory, and do so while ensuring that the process can only access its own address space. In this setup, each program is written and compiled as if it loaded an address 0. However, when a program starts running, the operating system decides where in physical memory it should be loaded and sets the base register to that value. In the example above, the operating system decides to load the process at physical address 32 kilobytes, and thus sets the base register to this value. Interesting things start to happen when process run. Now, when a new reference is regenerated by the process, it is translated by the processor into the following in the following manner. Each memory reference generated by the process is virtual address. The hardware in turn adds the context of the base register to this address, and the result is a physical address that can be issued to the memory system. To understand this better, let's trace through what happens when a single instruction is executed. Specifically, let's look at one instruction from our earlier sequence. The program counter is set to when the hardware needs to fetch this instruction, it first adds the value to the base register value, 32 kilobytes, to get a physical address. The hardware then fetches the instruction from the physical address. Next, the processor begins executing the instruction. At some point, the process then issues the load from virtual address 15 kilobytes, which the processor takes and again add to OK 74 until the desired content. Let's read first this part. Aside, software-based relocation. In the early days before hardware support arose, some systems performed accurate form of relocation purely via software methods. The basic technique is referred to as static relocation, in which a piece of software known as loader takes an executable and that is about to run, reroutes its addresses to the desired offset in physical memory. For example, if an instruction was a load from address 1000 into a register, okay, and address space of the program was loaded starting at 3000, not 0, the program thinks the loader would rewrite the instruction to offset each by 3000. In this way, a simple static allocation of the process. Static allocation has numerous problems. First and most importantly, it does not provide protection, as processes can generate bad addresses and thus illegally access other processes or even OS memory. In general, hardware support is likely needed for true protection. Another negative is that once placed, it is difficult to later relocate an address space to another location. First, okay, so specifically we'll need to okay, we have read this already. In this setup, okay, we have read this also. Yes, so hardware-based dynamic relocation. With dynamic relocation, little hardware goes a long way. Namely, a base register is used to transform virtual addresses into physical addresses. A bound or limit register ensures that such addresses are within the confines of the address space. Together, they provide a simple and efficient virtualization of memory. The load from virtual address 15 kilobytes, which transforming a virtual address into a physical address is exactly the technique we refer to as address translation. That is, the hardware takes the virtual address, the process thinks it's referencing, transform it into a physical address, and transforms into a physical address, which is where the data actually resides. Because this relocation of the address happens at runtime, and because we can move address spaces even after the process has started running, the technique is often referred to as dynamic relocation. Uh, hmm. Okay. So it is dynamic because it happens after the program started and not you know. Anyway, now you might be asking, what happened to that bound limit register after all? Isn't this the base and bounds approach? Indeed, it is. As you might have guessed, the bounds register is there to help with production. Specifically, the processor will first check that the memory reference is within bounds and make sure it is legal. In the simple example above, the bounds register would always be set to 16 kilobytes. If a process generates virtual address that is greater than or equal to the bounds, okay, or one that is negative, the CPU will raise an exception, and the process will likely be terminated. The point of the bounds is thus to make sure that all addresses generated by the process are legal and within the bounds of the process, as you might have guessed. We should note that the base of the and bounds registers are hardware structures on the chip, one pair per CPU. Sometimes people call the part of the process that helps memory management unit, MMU. As we develop more sophisticated memory management techniques, we'll be adding more circuitry to the MMU. A small aside about bound registers, which can be defined in one of two ways. In one way, as above, it holds the size of the address space, and thus the hardware checks the virtual address against it first before adding the base. Wait. A small aside about bound register can be defined in two ways. In one way, it holds the size of the address space, adding the base. The second way, it holds the physical address of the end of the address space. And thus the hardware first checks, adds the base, and then makes sure within bounds. Both methods are logically equivalent. For simplicity, we'll assume the former method. Example translations. Wait, let me see how much time. Okay, almost 40 minutes. Example translations. To understand address translation via base and bounds in more detail, let's take a look at an example. Imagine a process with an address space of size 4 kilobytes. Yes, unrealistically small. Has been loaded at physical address 16 kilobytes. Here are the results of a number of address translations. 0, 16, 1 kilobyte. Okay, just add 16 to each. Oh, okay. As you can see from the example, it is easy for you to simply add the base to the virtual address, which can rightly be viewed as an offset into the address space to get the resulting physical address. Only the virtual address is too big or negative will result in it to be a fault, causing an exception to be raised. As you can see from the example, hardware support, a summary. Let us now summarize the support we need from the hardware. Also, okay. First, as we discussed in chapter on CPU virtualization, we require two different CPU modes. The operating system runs in privileged mode or kernel mode, where it has access to the entire machine. Applications run in user mode, where they are limited in what they can do. Wait, let me just ask a question. I just have a question, like, for example, a database. I have in mind now Tiger Beetle, which I have seen that they use, for example, it's not like they are the only one doing it, it's a lot, but just anyway. If they use static allocation, like when the program starts, it allocates all the memory it needs and never allocates again since then. Wouldn't it be better to have a like Linux kernel fork that the memory management unit is as simple as like let me see. Here, for example, this dynamic allocation we studied here, which is based on bounds. It would be much efficient, and I have no idea. Wait, let me just ask it and let's see. Uh, just a little question. Let it think. I will read this later. Now just wait. Okay, 45 minutes. I'll just Okay, I'm back. So, what was this part about? Okay. First, as discussed in chapter on CPU virtualization, we require two different CPU modes. The OS runs in privileged mode or kernel mode, where it has access to the entire machine. Applications run in user mode, where they are limited in what they can do. A single bit, perhaps stored in some kind of processor, indicates which mode the CPU is currently running in. Upon certain special occasions, a system call or some other kind of exception or interrupt. Okay. The hardware must also provide the base and parallelism registers themselves. Each CPU that has an additional pair of registers, part of the memory management unit of the CPU. When a user program is running, the hardware will translate each address by adding the base value to the virtual address generated by the user program. The hardware must be able to check whether the address is valid, which is accomplished by using bounds register and circuitry within the CPU. The hardware should provide special instructions to modify the base and bounds registers, allowing the operating system to change them when different processes run. These instructions are privileged only in kernel or privileged mode. Can the registers be modified? Imagine the havoc a user process could wreak. What? What is havoc? Okay. Is there anything other than havoc that can be wrecked? Okay, I don't understand that. The hardware should provide special instructions to modify the base and bounds. Okay. If it could ever change the base register while running, imagine it. And it quickly flush such dark thoughts from your mind, as they are the ghastly stuff on which nightmares are made. Finally, the CPU must be able to generate exceptions in situations where a program tries to access memory illegally with an address that is out of bounds. In this case, the CPU should stop executing the user program and arrange for the operating system out of bounds exception handler to run. The operating system handler can then figure out how to react, in this case likely terminating the process. Similarly, if a user program tries to change the values of the privileged base and bounds registers, the CPU should raise an exception and run the tried to execute the previous instruction while using mode handler. The CPU must provide a method to inform it of the location of these handlers. A few more privileged instructions are thus needed. Let's see this. This structure is free list. The OS must track which parts of the free memory are not in use. So as to be able to allocate memory for processes, many different data structures can be used for such task. The simplest we will assume here is a free list, which simply is a list of ranges of the physical memory which are not currently in use. Okay. Operating system issues. Just as the hardware provides new features to support dynamic relocation, the OS now has new issues it must handle. The combination of hardware support and operating system management leads to the implementation of a simple virtual memory. Specifically, there are a few critical junctures where the operating system must get involved to implement our base and bounds version of virtual memory. What? Okay, so the OS must take action when a process is created, finding space for its other space in memory. Fortunately, given our assumptions, okay, it's quite easy for the operating system. It can simply view physical memory as an array of slots and track whether each one is free or in use. When a new process is created, the operating system will have to search a data structure option called free list to find room for the new address space and then mark it used. With variable sized address space, life is more complicated, but we will leave that concern for future chapters. Memory management. Let's look at an example. In figure 15.2, page 5, you can see the OS using the first slot of memory for itself, and that is that it has relocated the process from the example above into the slot starting at physical memory address 32 kilobytes. The other two slots are free. 16 kilobytes, 32 kilobytes, and okay. That free list consists of these two entries. Second, the operating system must do some work when a process is terminated. When it exists gracefully or forcefully killed because it misbehaved, reclaiming all of its memory for use in other processes or the operating system upon termination of a process. The OS thus puts its memory back on the free list and cleans up any associated data structures as need be. Third, the operating system must also perform a few additional steps when a context switch occurs. There is only one base and bounds register pair on each CPU, after all, and their values differ for each running program. As each program is loaded at a different physical address in memory, thus the operating system must save and restore base and bounds pair when it switches between processes. Specifically, when the operating system decides to stop running a process, it must save the values of the base and bounds registers to memory. In some per process structures, such as the process structure or process control block. Similarly, when the operating system resumes a running process or runs it for the first time, it must set the values of the base and bounds on the CPU the correct values for this process. We should note that when a process is stopped, not running, it is possible for the operating system to move an address space from one location in memory to another rather easily. To move a process address space, the operating system first deschedules the process, then the OS copies the address space from the current location into the new location. Finally, the OS updates the saved base register. Oblivious that its instructions and data are now in completely new spots in memory. Wait. Fourth, the OS must provide exception handlers or functions to be called as discussed above. The OS installs these handlers at boot time via privileged instructions. For example, if a process tries to access memory outside its bounds, the CPU will raise an exception. The OS must be prepared to take action when such an exception arises. The common reaction of the operating system will be one of hostility. It will likely terminate the offending process. The OS should be highly the OS should be highly protective of the machine it is running, and thus it does not take kindly to a process trying to access memory. Or execute instructions that it shouldn't be. Bye bye, Miss B. It's been nice knowing you. Figure illustrates much of the hardware OS instruction timeline. The first figure shows what the operating system does at boot time to ready the machine for use. And the second shows what happens when a process A starts running. Now note that its memory translations are handled by the hardware with no operating system intervention. At some point middle of second figure, a timer interrupt occurs and the operating system switches to process B, which executes a bad load. At that point, the OS must get involved, terminate the process, clean up freeing B's memory and removing its entry from the process table. As you can see from the figures, we are still following the basic approach of limited direct execution. In most cases, the OS just sets up the hardware appropriately and lets the process run directly on the CPU. Only when the process misbehaves does the OS have to become involved. Wait, so we have the fourth, we should, third, second, first. These are the issues. I feel like I understand this, but I don't memorize it. Okay, so here is like just a timeline. When a process wants to be run, the operating system takes control, finds some free chunk of memory in physical memory, loads the loads the process into it, updates the base registers values and like base and bounds registers, then let the program run. Like jump to its entry point main. Or like underscore start. Then what do we do? What do we do? The program runs on that stuff. When the program misbehaves and wants to access some illegal memory, the operating system, the CPU will catch it, raise an exception. The exception handler will be set by the operating system at boot time, and then it will jump to the exception handler. The operating system will take control, and it will terminate the process because it's misbehaved. And the developer must fix their own software. Okay, summary. Okay, let's read these because I didn't really read them. No, it's not these. Not these. Okay, so here is it. Initialize trap table. Remember the addresses of system call handlers, timer handlers, illegal mem access handlers, illegal instruction handlers. Oh. Okay. Start interrupt timer. Timer start interrupt after X millisecond. Free list. Also, okay. Wait. We had just a summary a little bit before. I have no idea what I'm reading right now. Okay. In this chapter, we have extended the concept of. Okay, let's read this before. To start a process A, allocate entry in process table, alloc memory for process, set base, return from trap into A. Store registers of A, move to user mode, jump into A's initial PC. Process A runs, fetch instructions, translate virtual address, perform fetch, execute instruction. Pass switch routine, save from trap, okay, build load is okay, move to kernel mode, kill the process, whatever. Okay, so in this chapter we have extended the concept of limited direct execution with a specific mechanism used in virtual memory, known as address translation. With address translation, the operating system can control each and every memory access from a process, ensuring the accesses stay within the bounds of the address space. Key to the efficiency of this technique is hardware support, which performs the translation quickly for each access, turning virtual addresses, the processor's view of memory, into physical ones, the actual view. All of this is performed in a way that is transparent to the process that has been relocated. The process has no idea its memory references are being translated, making making for a wonderful illusion. I have read this entire thing and didn't retain anything. Okay, so I have extended limited direct execution with specific mechanisms used in virtual memory, known as address translation. With address translation, the operating system can control each and every memory access from a process, ensuring the accesses stay within the bounds of the address space. Key to the efficiency of the technique is hardware support, which performs the translation quickly for each access, turning virtual addresses, the process view of memory, into physical ones, the actual view. We have also seen one particular form of virtualization known as base and bounds for dynamic relocation or dynamic. Base and bounds virtualization is quite efficient as only little more hardware logic is required to add a base register and virtual address checks at the address generated by the process is in bounds. Base and bounds also offer protection. The OS and the hardware combine to ensure no process can generate memory references outside its own address space. Protection is certainly one of the most important goals of the operating system. Without it, the OS could not control the machine. If processes were free to overwrite memory, they could easily do nasty things like overwrite a trap table and take over the system. Unfortunately, this simple technique of dynamic location does have its inefficiencies. For example, as you can see a figure. Because the processor and heap are not too big, all of the space between them is simply wasted. This type of waste is usually called internal fragmentation, as the space inside the allocated unit. Oh, I remember internal fragmentation term from the operating systems course we took. As the space inside the allocated unit is not all used, i.e. fragmented, and thus wasted. In our current approach, although there might be enough physical memory for more processes, we are currently restricted to placing another space in a fixed size slot, and thus internal fragmentation can arise. Thus, we are going to need more sophisticated machinery to try to better utilize the physical memory and avoid internal fragmentation. Our first attempt will be a slight generalization of base and bounds known as segmentation, which we will discuss next. Our first attempt will be a slight generalization of base and bounds known as segmentation, which we will discuss next. I really hate when. Why can't you just like type the full name? Just seeing this makes you feel extremely lazy. You have to read the program and see what are S and N are. I'm not reading that. I'm not doing the homework. Okay. Segmentation. Segmentation fault. How much time has passed? Okay. Wait. This one is 12 pages. I'm going to waste a little bit of time by playing type racer. Everyone thinks that- I was playing with dead people. Okay, 72 words per minute, which is good. Just 1 month ago, I was doing like average 60, sometimes even 50. Okay, 68 after a very bad start. 40, 50, 60. This is going to be tough. So I am okay, 64 in a very, very tough text. The first place also. Race again. I think this is going to be good. Very familiar words. Uh, 70. What? Okay, this was bad. Anyway. Segmentation. What is segmentation? Okay, so far we have been putting the entire address space of each process in memory. With the base and bounds registers, the operating system can easily relocate processes to different parts of physical memory. However, you might have noticed something interesting about these address spaces of ours. There is a big chunk of free space right in the middle between the stack and the heap. As you can imagine uh, from figure 16.1, although the space between the stack and the heap is not being used by the process, it is still taking up physical memory in where we allocate the entire address space somewhere physical memory. Thus, the simple approach of using a base and bounds pair to virtualize memory is wasteful. It also makes it quite hard to run a program when the entire address space doesn't fit in memory. Thus, base and bounds is not flexible as we would like it to be. And thus, the crux. How to support a large address space? How do we support a large address space with potentially a lot of free space between the stack and the heap? Note that in our examples with tiny pretend address spaces, the waste doesn't seem too bad. Imagine, however, a 32-bit address space 4 GB inside. A typical program will only use megabytes of memory, but it still would be but still would demand that the entire address space to be resident in memory. Okay. Segmentation, generalized base and bounds. To solve this problem, an idea was born, which is called segmentation. It is quite an old idea, going to at least for as far back as the very early 1960s or 60s. The idea is simple. Instead of having just one base and bounds pair in our MMU, why not have a base and bounds pair per logical segment of another space? A segment is just a contiguous portion of the address space of a particular length. In our canonical address space, we have three logical different segments called stack and heap. The segmentation allows the operating system to do so in place is to place each one of those segments in different parts of physical memory and thus avoid filling physical memory with unused virtual space, address space. Let's look at an example. Assume we want to place the address space from figure 16.1 into physical memory with a base and bounds pair per segment. See if, okay. Assume we want to place the address space from figure 16.1 into physical memory. With a base and bounds pair per segment, we can place each segment independently in physical memory. For example, there you see 64 kilobytes physical memory with those three segments and 16 kilobytes reserved for the operating system. Okay, so we have this, we have code, we have heap, and they are completely separate. Okay, as you can see in the diagram, only used memory is allocated space in physical memory, and thus large address spaces with large amounts of unused address space, which we sometimes call sparse address space, can be accommodated. The hardware structure in our MMU required to support segmentation and is just what you'd expect in this case, a set of three base and bound register pairs. Below shows the register values for examples. Okay, makes sense. You can see from the figure that the code segment is placed at physical address size. Okay. It tells the hardware exactly how many bytes are valid in the segment. Let's do an example translation. Using the address space in figure 16.1, assume a reference is made to virtual address 100, which is the code segment. As you can visually see in figure, okay, 16.1. Okay. When the reference takes place, say an instruction fetch, the hardware will add the base value of offset onto the segment, 100 in this case, to arrive at the desired physical address. It will then check the address with 10 bounds. Find the it is and issue the reference to physical memory address. Now let's look at an address in the heap. Virtual address again to refer to figure 16.1. If we just add the virtual address 4200, okay, which is not in the correct physical address. What we need to do is extract the offset into the heap, which bytes in the segment are address. What? Wait. Let's look at an address in the heap. Virtual address 4200 again. If we okay, let's see. Wait. 12, 6, 36 is here, around here. So it is here. Oh wait, this is the actual physical. Okay, so the address is here. Virtual address, okay. If we just add the virtual address to the base of the heap, what we need to first do is extract offset into the heap. Because the heap starts at virtual address 4 kilobytes, this offset is actually okay. Then we check the offset, okay, it makes sense. And add it to the base register of physical address. Makes sense. What if we try to refer to an illegal address, which is beyond the end of the heap? You can imagine what will happen. The hardware detects that the address is out of bounds, trapped into the operating system, likely leading to termination of the offending process. And now, the origin of the famous term that all C programmers learn to read: segmentation violation or segmentation fault. Which segment are we referring to? The hardware uses segment registers during translation. How does it know the offset into a segment? And to which segment an address refers? One common approach, sometimes referred to as an explicit approach. The hardware uses segment registers during translation. How does it know the offset into a segment? Which one common approach, sometimes refers as an explicit approach, is to chop up the address space into segments based on the top few bits of the other virtual address. If we use our top 2 bits of our 14 virtual bits, virtual address, virtual virtual address to select the segment, our virtual address looks like this. Oh, wait. In our example, then, if the top 2 bits are 00, the hardware knows it's a virtual code segment. It's a heap. If it is 1, wait. If the top 2 bits are 01, the hardware knows the address is in the heap and thus uses the heap base and bounds. Let's take our example heap virtual address from above and translate it to make sure this is clear. The virtual address in binary form can be seen here. This is 16-bit. What? Okay, we are in 16 bits. One, two, three, four, five, six, 7, 8, 9, 10, 11, 12, 13, 14. Okay, this is just 14 bits, whatever. As you can see from the picture, the top 2 bits tell the hardware which segment are we referring to. The bottom 12 bits are offset into the segment. Okay, thus the hardware simply takes the first 2 bits to determine which segment to register to use, and then takes the next 12 bits as offset into the segment. Wait. By adding the base register to the offset, the hardware arrives at the final physical address. Note the offset. Wait, by adding note the offset eases the bound checks too. We can simply check if the offset is less than the bound. If not, the address is illegal. Thus, if base and bounds were arrays with one entry per segment, the hardware would be doing something like this to obtain the desired physical address. Get top 2 bits of 14-bit virtual address. In our running example, we can fill in values for the constant above. Sigmas could be set to segshift 12, offset mask to which isn't this a no op? Because this is FFF, which is 11111. 1 and 1 is 1, 0 and 1 is 0. Wait. Well, maybe it depends per case, I think. You may have noticed that when we use the top 2 bits and we only have 3 segments, code heap stack, one segment of the address space goes unused. To fully utilize the virtual address space and avoid an unused segment, some systems push code in the same segment as the heap, and thus use only one bit to select which segment to use. Another issue with using the top, I feel tired, I can't continue doing this. Maybe I'll do it tomorrow. 2 hours, I think that's it for today.